In this video, we're going to do our third example using trig substitution to evaluate an integral. The integral we are given is the integral is equal to dx divided by the square root of 25x squared minus 4. We're given this constraint, and that really just keeps the radicand, the piece under the radical in the denominator, it keeps it positive or greater than 0. Now, because we have a variable squared minus a constant squared, we know we're using this pattern. This would be our reference triangle, and we're going to use this secant substitution. Of course, you might notice we have this extra coefficient in front of x squared. So in this situation, we need to rewrite that radical first. I need to think about a different way to interpret this. So I have 25x squared minus 4 under my radical. Now I need to get rid of that coefficient 25. So I'm going to factor GCF, and that leaves me with x squared minus, if I factor 25 out of 4, that gives me 4 over 25. I can take the square root of that 25, and I've got 5 square root of x squared minus 4 over 25. Now, keep in mind, this value needs to be a constant squared. So the root of 2 would be, the root of 4 would be 2, and the root of 25 would be 5. So this is the same as 5 times the square root of x squared minus 2 over 5 squared. So now I really have it in this format, which I can match up with my rules that I use. And I know I'm going to choose secant, and I'm going to choose secant with an a value of 2/5. A is going to equal 2/5. And if I am to write that out, we would say secant of theta equals x over a, x over 2/5. So let's go about determining our substitution. I'm going to erase some of this here. So I've rewritten my integral, and given that secant equals x over 2/5, I can multiply by that 2/5 and say, well, x equals 2/5 times secant theta. At this point, I can take the derivative. Dx d theta is 2/5 tangent theta secant theta. And then again, we multiply by that d theta. So I have my x value and I have my dx value. My dx value is going to substitute in here for the numerator. So before I substitute, rather than just plugging this 2/5 secant theta in for the x, I prefer to do a little manipulation first. So x squared minus 2/5 squared, well, that's the same as 2/5 secant theta squared minus 2/5 squared, or 4 over 25 secant squared theta minus 4 over 25. If I factor that GCF out, I'm left with secant squared theta minus 1, and we all know that secant squared theta minus 1 is equal to tangent squared theta. And for the sake of saving some space on my screen, I'm going to bring that up here. So we said that was equal to 4 over 25 tangent squared theta. So my integral up here, I can now rewrite that as 1/5. The integral of dx is now 2/5 tangent theta secant theta d theta. And my denominator, x squared minus 2/5 squared, that becomes 4/25 tangent squared theta. And that, of course, was under a radical. So if I am to square root the denominator, I have 1/5. And I'll actually go ahead and take this 2/5 and pull it out in front. So that gives me 2/25 of the integral of tangent theta secant theta over 2/5 tangent theta. And we are technically supposed to write our absolute value bars. However, we are specifying that tangent theta is greater than 0 or positive for any theta that's in the open interval between 0 and pi over 2, right? So we're specifying that, hey, we're going to only be dealing with positive numbers, so we don't need those absolute value bars. Pulling that 2/5 out in front, that's going to simplify to 1/5. 2/5, the reciprocal, that would be 5 over 2. So I've got 1/5, the integral of tangent theta secant theta over tangent theta. And of course we have our d theta at the end. I left that off on the step above. The tangent thetas cancel. I have 1/5, the integral of secant theta d theta. At this point, this is a fairly easy integration, and if we go to our table, number 95 from our table of integrals, we will see that the integral of this becomes the natural log of the absolute value of secant theta plus tangent theta plus c. So knowing this came from the table. That's where we got natural log of secant plus tangent. So our last step is to convert everything back into x's. Here I have thetas. I did a substitution to create that theta, so I need to substitute my x values back in. So I'm going to give myself some more space, and we're going to consider our reference triangle that we created. So theta down here in the corner, the adjacent side was 2/5, my hypotenuse was x, and the vertical opposite side is x squared minus that 2/5 squared, and that's found by the Pythagorean theorem, but also the way we set it up. We said that secant theta would be equal to x over 2/5, or rather 5 over 2x. And tangent theta, we have that in our answer. Tangent is opposite over adjacent. So that is the square root of x squared minus 4 over 25 divided by 2/5. Remember, dividing by 2/5 is the same as multiplying by 5/2. So I'm going to just clean that up here a little bit. So that would be the same as 5 square root of x squared minus 4/25 over 2. And to make it look more like our original problem, I can multiply that 5 back through. Once it goes into the square root, it would actually be the square root of 25x squared minus 4 over 2. So I know what tangent is equal to, I know what secant is equal to, and those are in terms of my reference triangle. So my answer here, my final answer, is going to be 1/5 times the natural log of 5x over 2 plus the square root of 25x squared minus 4 over 2 plus c. That's my third example using a trig substitution to evaluate an integral. So I've done one of each of our 3 types of substitutions that we can use. As always, email me if you have any questions.